Today we're going to talk about some proportions in solution mixtures. So here is our learning target: to understand the properties that describe solutions in terms of concentration, solute, and solvent. In order to do that, we are going to need to be able to calculate the concentration of a solution and to relate the concept of parts per million to relevant environmental issues. Now, you remember of Grand Lake when they closed down the beaches of the lake, okay? Because they have something, they take measurements of the water and they're looking for amounts of algae that's in the water and so many parts per million or parts per billion. Okay, so that's where we're seeing some of these because they're very, very small amounts. Okay, we deal with percentages a lot, don't we? Well, what a percentage is actually is it's just a part per 100. So if you have 6%, you have 6 parts per 100. If you have a 90%, you have 90 parts per 100. Okay? So we're going to learn about some of these concentrations. And here's a big thing to understand, that the concentration is the amount of the solute over the amount of the solution. Okay? And I believe when we did this in the video, you would then multiply it by different things, like to parts per million, you'd multiply it by 10 to the 6, I believe. Parts per billion, you'd multiply it by 10 to the 9th. But the generalization is amount of solute, amount of solution is the concentration. Now, we said amounts because we can't give you an actual label because it's different. Looking at this table, this is the one I just gave you. If we have, and most of the time we'll be dealing with mass per volume, which is this guy right here, okay? Most of the time we'll be dealing with mass per volume. So you're going to see that our label for mass per volume in parts per million is going to be milligrams per liter. Parts per billion, micrograms per liter. And I've even given you the stair steps here. So here is, here is the base, whether it's liters or grams. Here's the base. Then we have milli right there, micro, nano, pico. And how many jumps? And obviously, when we're jumping that way, we're jumping to the right, correct? So that's just some metric system conversion stuff review, okay? So how are we going to use this particular material? Well, here's my first example. Go ahead and write this example down, and then we're going to work it. My example says, an NaCl solution has a concentration of 132 parts per million. What mass of NaCl is contained in 250 milliliters of solution? So as I'm looking at this, I need to take my 132 parts per million, and I look at my data table, which was a couple of slides, well, this slide right here, and since I have a mass of NaCl and a volume, I'm going to look at the mass and volume section of my table, and I see that parts per million are milligrams per liter, right? So I come up here, I'm changing my label from parts per million now. I'm changing it to milligrams per liter, because that's what my chart told me to do. Now, once I have this in milligrams per liter, I'm trying to figure out the mass of the NaCl in this solution? Well, I have to do some conversions because I don't want this into milligrams, I want this into grams. I don't want this into liters, I want this into milliliters. So I've got to convert this into grams and milliliters. Well, it's really pretty simple because my first conversion box I'm going to put up, I'm going to convert it into grams. Well, I need milligrams to cancel, so I'm putting that on the bottom. And I know that 1,000 milligrams is equal to 1 gram. So I've now converted that into grams per liter, right? I don't want liter, I want milliliter. So I'm going to add on another conversion box. I want liter to cancel, so I'm going to put 1 liter up top. And 1 liter is equal to 1,000 milliliters. So now I have converted this into grams per milliliter. And when I do my math, I come up with a value of 1.32 times 10 to the negative 4. So I took my 132 divided by 1,000 divided by 1,000 again. Now, why did I do that? Well, because I know that my concentration is equal to the amount of solute divided by the amount of solution. Well, my concentration I just got. My concentration is 1.32 times 10 to the negative 4 grams per milliliter. I want to calculate my amount of solute. I have how much solution I need, don't I? 250 milliliters. So if this right here is X, can I solve that? Absolutely. When I solve that, I'm going to multiply 250 by the 1.32 times 10 to the negative 4th. So when I solve that, I got X. X is equal to 0.033, and that's going to be grams NaCl. How did I do that? Well, I took the 1.32 times 10 to the negative 4th, and I multiplied that by 250. Okay, so I multiply both sides. So that cancels. Multiply this side by 250 ml. My milliliters cancel, leaving me with grams. Multiplied those together. I got 0.033 grams of NaCl. And that was good because if I look right here at my 250 only has 2 sig figs. So my answer should only have 2 sig figs, and it did. Okay? So we're going to work a couple more of these. Okay? Here's my next one. Here's my next one, and it's once again dealing with this 132 parts per million. Well, based on my chart again, okay, that was milligrams per liter. So once again, I'm going to do my stuff here, and it's exactly like I just did on the other one. I've got to get it to grams per milliliter. So I take my milligrams. Now I've got it into grams. I take 1 liter, 1,000 milliliters. Now I got it into grams per liter. Since it's the same one, I use the same number, so it's still going to be that 1.32 times 10 to the negative fourth grams per milliliter. Now, what's different with this one? What's different with this one is I'm going to take my concentration. I'm going to take my concentration as 1.32 times 10 to the negative 4 grams per ml. This time, I have the mass given to me. So my mass of my solute is 0.024 grams, and I don't know what my amount of solute is, or excuse me, my amount of solution. So I need to multiply both sides by x. So when I do so, that cancels. My x is right here. So x times 1.32 times 10 to the negative fourth is equal to 0.024. Then I'm going to divide both sides by my concentration. My grams are going to cancel because I got one on top, one on the bottom. Being on the bottom of the denominator is going to give me my label is in milliliters. So I'm going to take 0.024, and I'm dividing that by 1.32 times 10 to the negative fourth, and I come up with a value of 181.81 repeating. Now I go back to my problem, and I look at the problem, and my problem tells me that I only have 2 sig figs. So I need to have my answer in 2 sig figs. Need a placeholder. So what volume of solution? It'll be 180 milliliters. Questions about that one? Here's our next example. Okay, this one's a little bit different because now we have a percentage. So I'm going to show you a percentage here. So I got 5.6% solution. Now when I go way back to my chart, not that far way back, When I come back here to my chart, let me get this out of my way. I don't know why all that junk's on my chart here. But now I'm dealing with percent. I'm still dealing mass volume. I'm dealing with percent. So it tells me grams per 100 milliliter. So I come back here to my percent, and I take that percent out of there, and I put in there grams per 100 mLs. That's what my chart told me. So 5.6% is really 5.6 grams per 100 milliliter. Well, that's my concentration. So my concentration is equal to my, not necessarily my mass, my amount. Let's go. My amount of solute over the amount of the solution. I have 25 milliliters of solution, right? So I can replace that by my 25 mLs. I'm making sure that my labels are the same. I could have to change that. So I made sure my labels are the same. So my labels are the same. So my amount of solute is my unknown. Once again, nice and easy. Can I solve for x? I hope so. You know your algebra. I multiply both sides by 25 milliliters. Multiply this side by 25 milliliters. I get that to cancel. So x is going to be equal to 5.6 times 25 milliliters, and divide that by 100, and I get a 1.4. Now what's my label going to be? Well, my milliliters cancel, so that leaves me with grams. 1.4 grams, and that's going to be grams of NaCl. What do you think? We'll run through another percentage one because this is just, like I said, just a tad bit different. This is 5.6% again. So I know that I'm dealing with mass again and volume. So my percent tells me with mass and volume to do grams per 100 mLs. Now, when I do this, this is equal to the amount of solute, in this case, is what was given, the 0.75 grams. So I'm trying to now find the volume. So that's my x. So what I have to do is I have to multiply both sides by x. So that cancels. So x times 5.6 grams over 100 milliliters is equal to 0.75. So knowing my algebra, in order to get this by itself, in order to get this guy by myself, I'm going to multiply by the inverse of it. So what I do to one side, I'm going to do to the other. Let me just do this a little bit different. Grams. I'm going to put my box in here. And I have that 100 mLs, and I have that 5.6 grams. So basically what I'm doing is I'm going to take that 0.75, multiply it by 100, and then divide it by 5.6. When I did that, I came up with a value of 13.393. Okay, 2 sig figs, 2 sig figs. So my x is going to be equal to 13. Grams cancel, leaves me with 13 milliliters. Now, my final problem here, it's a bit of a lengthy one. Okay, it's a bit of a lengthy one. Go ahead and copy this because you're going to see stuff like this on WebAssign. So get this in your notes so you can see how to work it. A sample of water is analyzed and found to have 48.0 parts per billion of arsenic. If a person were to drink 1 liter of this water per day for 2.3 years, what is the maximum amount of arsenic they could accumulate in their body? Okay, so in this particular question, I am trying to figure out how much arsenic is in this person's body. So I start out with 48.0 parts per billion. Now, when I'm dealing with ppb, I look at my data table, and it tells me that parts per billion are going to be labeled in micrograms per liter. Well, I look back up here and I say, okay, I want in liters. That's great. Okay? That's great. I want it in liters. However, when we're talking about the amount, I want that into either milligrams or grams. In this instance, I'm going to put it into grams. So I have to make a conversion to get this into grams per liter. Now, that's going to be a really, really small number. All right? So, I know that if I have 1 milligram, that is equal to 1,000 micrograms. Okay? I can look on my table and my stair jumps. So that's, I've converted now into milligrams. I can go one step further, and I know that 1,000 milligrams is 1 gram. So now I've converted this into grams per liter. So I take my 48.0, I divide it by 1,000, and I divide it by 1,000 again to do my conversion, and that gives me 4.80 times 10 to the negative 5. My label is going to be grams per milliliter. So that's my concentration. We okay with how I did that? Just a metric conversion. Oh, it is liters. My bad. It's not milliliters, grams per liters. So, every liter I drink, I get that many grams. Now, what we have to figure out, okay, what we have to figure out is how much will be in the body. So I take that concentration of grams per liter. Now this person drank 1.0 liters a day, right? Correct? So, once I do that, if I multiply this by 1, that this person would have 4.80 times 10 to the negative 5th grams every day. Well, how many days are in a year? 365. So, if I have 1 year, that's 365 days. So now, if I multiply that by 365, which I will do, it tells me that I have a value of 0.01752, and that's going to be grams per year. Running out of room here. How many years? 2.3. So I now multiply it by 2.3 years, and I come up with a value with 2, 3, 2 sig figs. I come up to a value of 0.040 grams, and that's going to be, I'm going to move my little recorder, that's going to be grams of arsenic. So this particular individual drinking 1 liter of water for 2.3 years, 1 liter per day for 2.3 years, will have accumulated 0.040 grams of arsenic over those 2.3 years. Okay?